Hello everyone, my name is Marc Guevara. I work as a postdoctoral researcher at the Barcelona Supercomputing Center, and in this video I'm going to show to you the results of a project that we performed under the framework of the Copernicus Atmosphere Monitoring Service, CAMS for short, and which consisted on quantifying the impact of the COVID-19 restrictions on European primary emissions. More specifically, I'm going to show to you how we made use of artificial intelligence techniques and CAMS products to compute our results. So, as all of you know, in order to contain the spread of the COVID-19 disease, European governments were forced to implement mobility restriction measures, which ranged from light social distancing to strict lockdowns, and which resulted in an unprecedented drop of atmospheric emissions. Several studies, including CAMS initiative, have assessed the impact of COVID-19 on air pollution through the use of satellite observations. However, a complete understanding requires also quantifying the reduction in primary emissions to understand, for instance, how individual pollutant sectors such as road transport, aviation, or the manufacturing industry were affected by the restriction, and also to develop a specific CAMS emission products that can be later used for air quality modeling purposes. To this end, the objective of our project was to develop a dataset of daily, country, and sector-dependent emission adjustment factors attributable to the COVID-19 measures, which could be later combined with the CAMS European emissions to perform emission analysis on the one hand and also air quality modeling activities on the other. The study was focused on those pollutant sectors most affected by the COVID-19 restrictions, including road transport, aviation, shipping, residential and commercial combustion activities, and the energy and manufacturing industry sectors. In terms of methodology, we followed a data-driven approach to develop the emission adjustment factors, in which changes in emissions were assumed to follow changes observed in measured time series representing the main activities of each sector, such as number of flight operations in airports, measured road traffic counts, or energy consumption statistics, among others. The adjustment factors were constructed as a ratio between the measured activity data for a given day and the value of this activity without the COVID-19 influence, or what we call the baseline. And the selection of this baseline was performed using two different approaches mainly, and depending on the sector of study. A first approach consists on considering activity data values from a pre-lockdown period that could be, for instance, the first month of 2020 before lockdown started, or the closest date from the previous year, 2019. A second approach was to consider activity data values derived from a business-as-usual 2020 scenario, or in other words, from a scenario in which we assumed that COVID-19 did not exist. And for that, we made use of artificial intelligence. To illustrate how we made use of each type of baseline, I'm going to explain to you the procedure that we follow to construct the emission reduction factors for the road transport and the energy industry sector. For the first case, changes in road traffic emissions during the COVID-19 period were computed considering as a baseline measured traffic counts from the closest date in 2019. These two plots here shows an example of the adjustment factors that we compute for the United Kingdom and Spain for January to July 2020. The two cases show how the decrease in traffic emissions started to occur during mid-March, end of March, coinciding with the implementation of the national lockdowns to reduce mobility and social interactions. Reductions of up to 70% were observed in UK, for instance, which remained almost unchanged until the end of April. By that time, traffic activity started recovering, coinciding with the relaxation of the mobility restrictions, and this trend was confirmed during May, June, and July with a steady recovery. A similar approach was followed for all the other pollutant sectors except for the energy industry sector, for which we had to face an extra challenge. As shown in the plot on the left side, which illustrates the relationship between daily outdoor temperature and the electricity consumption in the United Kingdom for the years 2015-2019, changes in electricity consumption are linked to temperature fluctuation. The plot shows how the lower the temperature is, the larger the electricity consumption, mainly due to an increase of the energy demand for space heating purposes. At the same time, and according to the European State of the Climate Report compiled by Copernicus, 2020 was the warmest year on record in Europe. Considering these two facts, a direct comparison between 2020 and pre-lockdown electricity demand levels would have been influenced by the confounding effect of meteorological variability. In other words, the difference in electricity consumption that we would have computed if we had followed the same approach previously presented for the road traffic sector would have not been affected by COVID-19 restrictions only, but also by the changes in temperature occurred between 2019 and 2020. In order to overcome this limitation, we made use of artificial intelligence to estimate a time series of 2020 business-as-usual electricity demand, or in other words, without the lockdown effects. This business-as-usual electricity demand was computed using a gradient boosting machine model trained and tuned independently for each country and using daily data from January to July between 2015 and 2019. As inputs, we consider daily outdoor temperature derived from the Copernicus Era 5 reanalysis, daily electricity consumption derived from the ENSOE European platform, the Julian date, day of the week, and a Boolean feature indicating the country-specific bank holidays. While the training and tuning of the gradient boosting machine models were performed from 2015 to 2019, we used the first 2 months of 2020 before lockdown started to test the performance of the models that we developed. The following figure shows an example of the real and business-as-usual 2020 electricity consumption computed for Spain. The first one is represented with the blue line and the second one with the green line. It is observed that during the first week of the year, with the absence of the COVID-19 restrictions, the modeled business-as-usual electricity demand is capable of reproducing the observed levels with the correlations that are up to 0.98 and a normalizing mid-bias of 2%. Differences between the two scenarios, which are shown in the bottom part of the plot, starts to appear with the beginning of the restrictions during the second week of March. As mentioned before, a specific gradient boosting machine model was trained and tuned for each European country. And this plot here shows the machine learning derived adjustment factors for a selection of country. As expected, the resulting trends are consistent with the national lockdown calendars and restriction levels implemented in each country. We can see how the largest reductions are reported for Italy, the country where the first European national lockdown was implemented, while the lowest ones are observed for Sweden, where only national recommendations, such as relatively soft social distance measurements, were provided to citizens. The daily and country-dependent adjustment factors that we compute for each of the pollutant sectors considered in this study were combined with the CAMS European Regional Emission Inventory, a dataset that reports annual emissions for priority air pollutants and greenhouse gases at a spatial resolution of about 6 kilometers by 6 kilometers. The CAMS European regional emissions are constructed and maintained by the Netherlands Organization for Applied Scientific Research, and it is used within CAMS to support several European air quality modeling activities. In order to quantify the impact of the COVID-19 on primary European emissions, the resulting COVID emission adjustment factors were compared against the 2020 business-as-usual scenario, in which emissions were basically assumed to follow the tendency observed during the previous years. This twin video here shows a comparison of the daily nitrogen oxide emissions computed for the business-as-usual and COVID-19 scenarios. it is observed how the reduction of primary emissions is particularly visible in Italy, France, and Spain during April, where the most restrictive nationwide lockdowns were implemented. We can also see that the largest reductions occur in main interurban roads as well as urban areas where road traffic emissions dominate. It is worth mentioning that these three countries, together with Germany and the United Kingdom, represented more than 65% of the total nitrogen oxide emission drops occurred in the European Union plus UK between January and July 2020. The combination of the adjustment factors with the CAM's European Regional Emission Inventory was useful not only to spatially and temporally represent the changes in emissions, but also to quantify the contribution of the different pollutant sectors to the total emission reductions. These two plots here show the evolution of the weekly average nitrogen oxides and particulate matter emissions in the European Union plus UK, discriminated by sectors. It is observed how the drop in nitrogen oxide emissions in the left side is mainly driven by changes in the road transport emissions, while in the case of particulate matter, the changes in total emissions is almost negligible, as these emissions are dominated by residential wood combustion activities, which is an activity that actually experienced a slight increase during the lockdown since people were forced to spend more time at home. To summarize, we developed a dataset of CAM's COVID-19 emission adjustment factors to help quantifying the impact of the lockdown policies during the COVID-19 pandemic. Specific adjustment factors are provided by country, pollutant sector, and day of the year to reflect the heterogeneous implementation of the restrictions and their effect. We saw that the adjustment factors were constructed using a data-driven approach, which basically combines the use of traditional proxies such as traffic counts with artificial intelligence techniques. The resulting dataset can be combined with the CAM's European emission to help the scientific community in air quality modeling. In terms of key results when comparing the business as usual and the COVID-19 emission results, we saw largest emission reductions were found in Italy, France, and Spain, and also we saw large reductions in urban areas and main interurban corridors. We also found a large contrast between the reductions in nitrogen oxides and particulate matter. I hope you found what I shared with you interesting, and of course do not hesitate to contact me if you have any comments or doubts.